Level 3 is called coin flip. Now this is a coin flipping game where you need to build up your winning streak by guessing the outcome of a coin flip. And we need to do this 10 times in a row to pass this challenge. So let's take a look at the code. So we can see the contract starts by declaring a public variable for consecutive wins, which we can call to see how many consecutive wins we have. The constructor of the contract, which if you remember runs once and only once when the contract is first deployed, will set the consecutive wins to 0. Our challenge now is to increase the consecutive wins variable to 10 in order to win. If we scroll a bit further down, we can see the flip function, which is how we guess which side of the coin it's going to land on. Now we can see the flip function takes a guess, which is either true or false. And just below that, we've got a variable called block value. Now this takes the block number, subtracts 1, and finds the block hash for that block. If we look a bit further down, we can see a variable called coin flip, which is the block value divided by factor. You might notice factor from earlier on in the code, where it's set as a large number. We then have a ternary operator to see if coin flip equals 1, then it's true, or if not, it's false. And if the side that we guess is correct, the consecutive wins increase, and if not, they're reset to 0. So what the contract is trying to do is it's trying to create an element of randomness for the coin flip. This is so it will be difficult for us to guess. But what this type of contract fails to account for is the fact that we can see all of the factors of the randomness and that these factors will be calculated in the same block as any potential transaction we put in. So how can we hijack the logic here to be able to guess exactly which side of the coin this is going to land on with absolute certainty every single time? To do this, we're going to create an attacker contract to attack this contract on the blockchain. We're going to use the Remix IDE. So head on over to remix.ethereum.org, create a new file and call it coinflip.sol. Go back to the Ethernaut page, copy over the smart contract and paste it into the coinflip.sol file. At the top, you need to replace the OpenZeppelin SafeMath line of code with the URL from the GitHub. I'll include this URL in the description below. The reason why we're doing this is because we don't have the SafeMath contract stored locally in this Remix environment. We need to reference it from GitHub. The next step is to go ahead and update your Solidity version at the top to 0.8.0. Click the compile button on the left-hand side and make sure everything runs smoothly. You should only have yellow warnings, no red warnings. Now that's done and successfully compiled, we can get started on our own attack contract. This contract will guess the flip every single time. So go back to your files and create a new file called coinfliphack.sol. So let's start off by including the SPDX license identifier from MIT, and then by declaring our Solidity version with Pragma Solidity 0.8.0. Next, we want to import the coin flip contract we set up. And after that, we're importing the SafeMath contract, which is also in the description below. The reason why we use SafeMath is so that the calculations we make for the randomness are safe. There's some characteristics as a part of the SafeMath contract that protect things like underflow and overflow, which we'll get into more in the later videos. After this, we're going to create the contract, which is called coinfliphack. And as part of this, the first thing we're going to do is going to import SafeMath for the unsigned integers that we're using. We're then going to create a new variable of a type coinflip, and it's going to be the target contract. And we're also going to import the factor from the coinflip contract so we can copy the randomness of the original contract. Now let's set up a constructor. With this constructor, we're taking in an address of the target contract, and this is going to run once when we set the contract up, meaning we can give it the address of the contract we want to target when we set up the contract. And to do that, let's create target contract equals coinflip, passing through the target contract URL that we give the constructor on deployment. Next up, we're creating a function called guessFlip, and this is going to return a Boolean. And as part of that, let's import the logic from the original coin flip contract. So this is so that we can guarantee that we can copy the randomness from the original contract when we're guessing the coin flip side. And then we're going to call the target contract, and we're going to flip, and we're going to pick the side that we've calculated using the exact same logic that the original coin flip contract uses. Now, if you've done this correctly, the logic should copy over, and the side that you pick here will be the exact same side that the contract calculates, meaning every single time you run this guess flip function, you will guess the exact same coin flip side as the original contract will calculate. So let's give it a go. Head over to the compiler and let's compile the version of this coin flip hack contract. If you've done it correctly, you should only have yellow warnings, no red warnings. And once that's done, head over to the deploy panel. Underneath environment, select injected web3. This should connect to your MetaMask wallet, and you should be ready to deploy this contract onto the testnet. Go ahead and select the coin flip hack contract. And in order to get the address of the instance, let's head on over back to Ethernaut. Let's press Ctrl-Shift-I, and we should have the instance address down here. If you don't have it there, go back up, select Get New Instance to grab an instance of this contract. Once you have the instance, let's head on back to the Remix environment, and where we're deploying the target contract, let's go ahead and paste that target contract there and click Deploy. Next, you want to go ahead and confirm this transaction. And what you're doing is you're deploying this coin flip hack contract onto the testnet blockchain for you to then call it, which will then attack the original coin flip contract. Okay, we can see that's all gone through. So let's scroll down on the left-hand side here and let's see our deployed contracts. We can see coin flip hack has an option for us to guess flip, which is the function we created here that will guess the flip of the original coin flip contract. But before we run that guess flip function, let's head on back to our Ethernaut instance and let's check the consecutive wins that we have by typing await contract dot consecutive wins. And once you run that, you will be able to see, once you expand the array, that we have 0 consecutive wins. Now let's return to the Remix IDE and let's go ahead and guess the flip. This will pop up MetaMask again. Go ahead and confirm that. And we can see here, the contract has gone through, the process has been mined, and we've guessed the flip. Now let's check if it was correct. Let's go ahead and run that same command again. So await contract.consecutive wins. And this should return an array where we have 1 consecutive win. So we guessed it correctly that time. Now I'm going to repeat this step 10 more times, and I'm going to return when I'm on 10 consecutive wins, and then we'll take it from there. So after running that guess flip function 9 more times, I now have 10 consecutive wins, meaning that my attacker contract managed to guess the correct side of the coin 10 times in a row without failing. And this was possible because the person who created the coin flip contract left all of the randomness logic in the contract for us to be able to exploit. So what are the key takeaways from this challenge? The key takeaway here is that when you're creating functions with randomness involved, do not try to create the randomness on your own using calculations on the chain itself. There are services like the chain link verifiable randomness function that will be able to create a random number for you without any attacker being able to see the logic behind the randomness itself. So I hope you learned something new in that challenge. Join us in the next video where we complete challenge number 4.